So, mixing ratios for gases. That means we're dealing with the gases in air, and those mixing ratios are usually expressed on a volume per volume basis. Here's an example, a common example, atmospheric carbon dioxide. Its concentrations are usually expressed in parts per million by volume, right? Volume of CO2 per volume of air, like liters of CO2 per million liters of air. That would be a part per million. Here's a plot of CO2 concentrations measured at Mauna Loa Observatory on the Big Island in Hawaii from the late 1950s through the early 2020s, and you can see the concentrations of CO2 going from 320 to 420 on the y-axis. But what are those units? Parts per million. That's the unit that we almost always hear used to describe concentrations of CO2 in the atmosphere. Can't get away from it, got to deal with it. Another example, this is just not tied to anything in particular, it would just be like cubic meters of benzene, a known human carcinogen, per billion cubic meters of air. Again, that would be cubic meters per billion cubic meters. That would be a part per billion. So, volume per volume mixing ratios for gases in air is truly a convention in environmental health and other sciences. However, you may sometimes encounter units written this way, like ppm parentheses v, or ppb parentheses v. And that's just the authors being explicit that this mixing ratio is on a volume per volume basis. All right, so let's do a dimensional analysis example with mixing ratios for gases. Here's the challenge. We want to go from a mixing ratio for a gas to a mass per volume concentration of that same gas. All right. So let's use CO2. Here's the information we're given. If we get the cursor over here. The global average concentration of carbon dioxide is 450 ppm. What is that CO2 concentration in milligrams per cubic meter? Assume a temperature of 25 degrees Celsius and pressure of 1 atmosphere. Okay. We might ask why, but we'll check this out. So let's use our technique of writing down our starting units first. So 450, some volume, we need some unit of volume. I chose liters. 450 liters of CO2 per million of that same unit. So again, we'll use liters per million liters of air. So 450 liters of CO2 per million liters of air, that's 450 part per million by volume CO2. That's where we're starting. Now where are we trying to go? We're trying to go here to milligrams of carbon dioxide per cubic meter of air. Whoa. All right, so somehow we have to get this volume of a gas to the weight of the gas. All right, let's start and see where it takes us. We began the prior dimensional analyses by dealing first with the numerator, but here let's deal with the denominator first and just get it out of the way. So we want to convert this liters of air to cubic meters of air. Well, we know there are 1,000 liters of air for every cubic meter of air. So we'll introduce that equivalency and we'll cancel out our liters of air. And so we've taken care of the denominator right away. Next step. Let's convert this liters of CO2 to moles of CO2. So bear with me here. We're just going to do this, and we're going to proceed with this this conversion step right now, and then we're going to go to slide 16, Now we're going to take a look at where this comes from. Okay, so we're going to convert our liters of CO2 to moles of CO2. You might remember from chemistry that a mole of a substance means there are 6.02 times 10 to the 23rd instances of that substance, like molecules of that substance. That is the definition of a mole, and that 6.02 times 10 to the 23rd, you might remember, is called Avogadro's number. Okay. So, at a temperature of 25 degrees C and a pressure of 1 atmosphere, 1 mole of a gas, in this case CO2, occupies a volume of 24.45 liters. And again, I'll show you where that comes from in a subsequent slide. But let's go with that now. So here we can now cancel out our volume of CO2, and we're to, I didn't mean to do that. We are now at liters of CO2. I'm sorry, we're at moles of CO2. But that's not what we want. We want milligrams of CO2. So to go from moles to grams of CO2, we can use the molecular weight of CO2, which is 44, right? 12 for carbon, 16 for oxygen, another 16 for the second oxygen. So that's 32 and 12. It's the molecular weight of CO2 is 44 grams per mole. So now we can cancel out our moles of CO2, and we're in grams of CO2. We're trying to get to milligrams, so we know there are 1,000 milligrams for every gram. Boom. And now we run through the math, and let's see, let's just do some other canceling. We've got 10 to the 6th in the denominator, and we've got a 10 to the 3rd and another 10 to the 3rd in the numerator. So those are together 10 to the 6th that are in the numerator, which will cancel out the 10 to the 6th in the denominator. And we're left with 450 times 44 divided by 24.45, which turns out to be 809.8 milligrams of carbon dioxide per cubic meter of air. Just fill in the conversions that were done. And then here is the conclusion. 450 part per, oh, that's a typo. 450 part per million, that's ppm, CO2 is equivalent to 809.8 milligrams of CO2 per cubic meter. Where, oh where, did this 24.45 liters per mole come from? Came from here, the ideal gas law. The ideal gas law allows us to link moles of a gas and the volume of a gas. Okay. In other words, the ideal gas law is the key to converting between the two units of gas concentrations, meaning mass per volume and volumetric mixing ratios. How does that work? Well, the ideal gas law describes the relationships among pressure, volume, moles, and temperature of a gas. Here's the ideal gas law. PV equals nRT. You've probably seen this before, like in a chemistry class. P is pressure, V is of the gas, V is volume of the gas, N is the number of moles in that gas, of that gas, R is the ideal gas constant, this is just a fixed value, a constant, and T is the temperature of the gas. So I'm going to use, there are lots of different units for pressure, there are lots of different units for volume. I'm going to use atmospheres for pressure and liters for volume. I just find that to be the most convenient, and so I'm going to stick with that here. And then the temperature in the ideal gas law has to be in Kelvin. Okay, so we can use the ideal gas law, and when we do, we can use it in combination with the molecular weight of the gas to calculate how much a volume of gas weighs. So here's our example. A mole of some gas, let's say any gas, is 6.02 times 10 to the 23rd molecules of the gas. Avogadro's number, as I said. Here's the question. What is the volume of 1 mole of a gas at 25 degrees C and 1 atmosphere of pressure? Here's our strategy. Rearrange the ideal gas law for volume. So we're going to rearrange this equation for volume. We're going to plug in the values for temperature, pressure, number of moles, and the gas constant. And we'll be able then to know the volume of a gas, the volume of a certain number of moles of a gas. Okay. So here we go. Rearranged. Let me get the yeah, okay. So I've rearranged the ideal gas law here. I've solved for volume, right? Just divided through by pressure and put it on the right-hand side. Now let's plug in what we know. Let's say 1 mole of a gas we're asked about. Bingo. Let's put in R, the gas constant that was given to us up here, 0.08206, very complicated units, liter atmosphere per mole Kelvin. So we put those in. And we need the temperature, which would be 298 Kelvin. That's because Kelvin degrees is 273 plus Celsius degrees. And then we need one more input, which is going to be the pressure, 1 atmosphere. So let's check our units. Let's see, we got atmospheres canceling out here. We've got moles in the denominator and moles in the numerator here, so those cancel out. And we've got Kelvin in the denominator and Kelvin in the numerator here. And so what units are we left with? We're left with the ones we want, which are liters. So we go do the math and we get 24.45 liters. What do we conclude? We conclude 1 mole of gas at 25 degrees C and 1 atmosphere occupies 24.45 liters of volume. It's true for any gas, not just CO2. So, how much does 1 liter of CO2 at 25 degrees C and 1 atmosphere weigh in grams? Well, here's our starting point, 1 liter of CO2. Here's where we're trying to go, grams of CO2. Let's put in the conversions at this temperature and pressure. 1 mole of CO2 occupies 24.45 liters. So we can cancel out our liter of CO2 because we now have it in moles. And we know that every mole of CO2 weighs 44 grams. So that can cancel out our moles. And now we're at grams of CO2. So we do the math. 44 divided by 24.45 is 1.8 grams of CO2.